Let me ask you something. Right now, while you're sitting there, how many things is gravity doing? Not out in space, not at the center of a black hole. Right now in this room, to your body. Most people say one thing. It's pulling me down, keeping me in my seat. And yeah, that's true. But that answer is so incomplete, it's almost a lie. Gravity is doing hundreds of things to you right this minute, and you don't notice any of them, the same way a fish doesn't notice water. Gravity is compressing the cartilage in your spine. It's pulling your blood downward, so your heart has to work harder to push it up to your brain. It's pressing the air against your eardrums. It's holding a column of atmosphere above your head that weighs roughly 10,000 kilograms. It's keeping the nitrogen and oxygen molecules you're breathing from drifting off into the vacuum of space. It's pressing the tectonic plate beneath your feet against the hot mantle underneath. It's bending the path of the Earth around the sun so you don't fly off in a straight line into the dark. It is, right now, making time tick slightly slower for you than for someone standing on top of a mountain. That's not poetry. Every one of those is a measurable physical effect. You live inside all of them every moment of your life, and you've never once felt them. So here's what I want to do. I want to peel this thing apart one layer at a time, starting from the simple and going deeper and deeper. And once you see all the layers, once you see the full portrait of what gravity is actually doing, we're going to do something reckless. We're going to switch it off. 1 second, just one tick of the clock, and then we're going to see what breaks. I promise you, it's stranger than you think. All right, layer 1, the obvious one. You're standing in a room. Gravity shuts off. What happens? You float. Obviously, your feet leave the ground. Everything on the table, the cup, the pen, the salt shaker, they all just drift upward a little bit. It's like being on the space station. Fun, right? Weightless. Like a dream where you can fly. Now hold on. I said drift upward. But why upward? If gravity is gone, there's no up and down anymore. Those words just lost their meaning, so why would you float up instead of just hovering in place? Here's the first thing people miss. You wouldn't just hover. Right before gravity turned off, the floor was pushing up on your feet. Newton's third law. You push down on the floor pushes up on you. The forces are balanced, so you stand still, but both forces are real. The instant gravity disappears, the downward pull vanishes, but the upward push from the floor doesn't vanish at the same instant, because your feet and the floor were slightly compressed, like tiny springs. They uncompress, that gives you a little kick upward, very gentle but real. More than that, your body was making constant micro-adjustments to stay balanced. Tiny muscle contractions in your legs, your ankles, your core, all of those were calibrated to fight gravity. The signals from your brain to your muscles travel at about 100 meters per second. It takes a few hundredths of a second for the gravity is gone news to propagate through your nervous system. In that fraction of a second, your muscles are still firing anti-gravity corrections. They push you in odd directions. You might tip forward. You might lean. Someone mid-stride would tumble because the whole walking motion is a controlled fall that depends on gravity being there to catch you. The blood in your veins is being pumped upward by your heart against gravity. Suddenly, there's no gravity to pump against. The blood pressure in your head spikes slightly. Your face flushes. The blood in your legs, which gravity was pulling downward, redistributes upward. This is exactly what happens to astronauts, by the way. Their faces get puffy, and their legs get skinnier. They call it chicken legs and moon face. In 1 second, you wouldn't see much change, but you'd feel it. A rush to the head, a warmth behind your eyes, and your inner ear, the vestibular system. You have these little chambers filled with fluid and tiny calcium carbonate crystals called otoliths. When you tilt your head, the crystals shift under gravity, pressing against hair cells that tell your brain which way is down. Remove gravity and the otoliths float. The hair cells get no signal. Your brain, which has relied on this signal every moment of your life since before you were born, gets confused, deeply confused. The room seems to spin even though nothing is spinning. You feel nauseous, disoriented. Some people would stagger. Some would grab onto furniture. It's the same sensation you get on a roller coaster at the top of a drop, multiplied by 10. Every animal on Earth with a vestibular system, which is essentially every animal with a backbone, feels this simultaneously. Birds in flight would be the most affected. A bird's sense of up and down is even more critical than yours. Their flight depends on it. A pigeon mid-wing beat would tumble. A hawk diving for prey would veer off wildly. Fish in the ocean would lose their sense of which way is the surface. Even insects, which use gravity-sensing organs called statocysts, would wobble. And think about the plants. This one is subtle. Plants know which way is down. Their roots grow downward, and their stems grow upward because of a process called gravitropism. Inside their cells, tiny starch granules called statoliths settle to the bottom under gravity, triggering chemical signals that tell the plant which direction to grow. Remove gravity, and the statoliths float. The chemical signals stop. The plant's growth compass goes blank. For 1 second, every root tip and stem tip on Earth briefly loses its sense of direction. This doesn't matter, of course, because 1 second is far too short for any visible growth. But at the cellular level, the chemistry hiccups. A tiny molecular stutter in every plant on the planet, all at once. I love that. A moment of collective botanical confusion. 1 second of weightlessness. Unpleasant for animals, imperceptible for plants, survivable for everyone. You might spill your coffee, though. The coffee, by the way, does something beautiful. It lifts out of the cup in a perfect sphere because without gravity pulling it down, the only force shaping the liquid is surface tension. And surface tension always wants to pull a liquid into a sphere. For 1 glorious second, there's a little ball of coffee hovering where your mug used to hold it. Then gravity comes back and it splashes everywhere. But for that 1 second, it's magnificent. All right, so that's layer 1. Floating people, floating coffee, confused inner ears, the part everyone imagines. Most people stop right here and think they've answered the question. They have not even begun. Let's step outside. The air you breathe. Why does Earth have an atmosphere at all? This is a question most people never ask, because the air has always been there, but it doesn't have to be. The Moon has no atmosphere. Mercury has essentially none. Mars has a thin wisp. Why does Earth have this thick, rich blanket of gas? Gravity. Gravity holds it down. An air molecule, let's say nitrogen, which makes up about 78% of our atmosphere, is not sitting still. At room temperature, a nitrogen molecule zips around at about 500 meters per second on average. That's fast. Very fast. About 1,100 miles per hour. Faster than the speed of sound, actually. Every molecule in this room is a tiny bullet ricocheting off the walls, off the floor, off other molecules, billions of times per second. Why don't they all fly away? Because the escape velocity from Earth's surface is about 11.2 kilometers per second, which is 11,200 meters per second. The average molecule is moving at 500. That's way below escape speed. But here's the thing. That's the average speed. In any gas, there's a distribution of speeds. Some molecules are slow, some are fast, and a tiny fraction are really fast. This is called the Maxwell-Boltzmann distribution. And the tail of that distribution reaches up to very high speeds. At any moment, a tiny fraction of air molecules near the top of the atmosphere do have enough speed to escape. And they do escape. Earth is slowly losing atmosphere right now. Today, just very, very slowly, hydrogen and helium, being the lightest, escape the fastest. That's why our atmosphere has very little hydrogen compared to the universe as a whole. So gravity's job is to keep the escape rate negligibly small. It's the leash on a billion energetic dogs. Cut the leash for 1 second. What happens? The entire atmosphere doesn't vanish. Not even close. In 1 second, even the fastest molecules can only travel about 10 to 15 kilometers. The atmosphere extends up hundreds of kilometers, and the bulk of it is in the lowest dozen or so. So the lower atmosphere mostly stays put out of sheer inertia. It hasn't had time to go anywhere. But 2 things do happen. First, the pressure gradient starts to dissolve. Right now, air is denser at sea level and thinner as you go up. This is because gravity stacks the air, compresses the bottom layers under the weight of all the air above. At sea level, the pressure is about 101,000 pascals, about 1 atmosphere. At the top of Mount Everest, it's a third of that. On an airplane at cruising altitude, it's a quarter. Remove gravity, and there's no reason for the air at the bottom to be more compressed than the air at the top. The atmosphere begins to equalize. Dense air at the surface starts to expand upward. Thin air at high altitude doesn't get replenished by subsiding gas from above. In 1 second, the change is tiny, maybe a few pascals drop at the surface, but it's measurable. Sensitive instruments would pick it up. Second, at the outermost edge of the atmosphere, the thermosphere and exosphere, where molecules are already spread incredibly thin and some of them are moving fast enough to barely be bound, those molecules leave. They're gone. They reach escape velocity because the velocity required to escape just dropped to zero. Any upward motion at all is enough. Earth permanently loses a thin shell of its outermost atmosphere. Not enough to notice in your daily life. Not enough to change the air pressure you feel. But it's gone. Irreversibly. And here's a beautiful subtlety. Weather patterns are driven by pressure differences. High pressure zones and low pressure zones. Wind is air moving from high to low pressure. If the global pressure field shudders, even slightly, it sends a ripple through every weather system on the planet. 1 second of gravity off wouldn't create a hurricane. But it would nudge existing storms. It would create a tiny perturbation in the atmosphere that would propagate for days, altering weather forecasts in ways too small for anyone to trace back to the cause. The butterfly effect, except the butterfly is an entire planet hiccuping. Layer 3. The oceans. Water is heavy. A cubic meter of seawater weighs a little more than 1,000 kilograms. The total mass of the ocean is something like 1.4 times 10 to the 21st kilograms. All of that water is held in its basins by gravity. Every drop in the Pacific, every molecule in the Atlantic is being pulled toward the center of the Earth. That's what gives the ocean its shape. That's what makes the surface, on average, follow the curve of the planet. Kill gravity, and the ocean is no longer being told to stay put. But the ocean wasn't just sitting there even before gravity turned off. Currents move water constantly. The Gulf Stream carries about 30 million cubic meters per second, flowing at maybe 1.5 to 2 meters per second in its core. The Antarctic circumpolar current, even bigger, moves 150 million cubic meters per second. Tides were pulling water toward the moon and the sun. Waves were cresting and crashing. All of that momentum doesn't vanish when gravity turns off. The water keeps moving in whatever direction it was already going. But now there's nothing pulling it back to the surface. A wave that was cresting at the moment gravity stopped, it keeps going up. The spray off the top of that wave just keeps flying. Coastal waters that were pressing against the shore relax. Not dramatically, not like a movie tidal wave in reverse, but subtly. You might see the waterline creep back 0.5 centimeter on a beach. You might see a strange bulge form on the open ocean where two currents converge and the water, with no gravitational pressure holding it flat, heaps up ever so slightly. And here's something that sounds like science fiction, but is pure physics. The ocean floor is under tremendous pressure. The deeper you go, the more water stacks above you, and the more crushing the force. At the deepest point, the Challenger Deep in the Mariana Trench, the pressure is about 1,100 atmospheres. That's over 1,000 kilograms on every square centimeter. Like having a small car balanced on your thumbnail. That pressure exists because gravity pulls the water down and stacks it up. Remove gravity, and the weight disappears. The pressure starts to drop. Now, it doesn't drop instantly everywhere. Pressure changes travel through water at the speed of sound, which in seawater is about 1,500 meters per second. The Mariana Trench is nearly 11,000 meters deep, so it takes about 7 seconds for the gravity is off message to reach the bottom. In our 1 second, the pressure relief only penetrates about 1,500 meters down. But in those upper 1,500 meters, here's what happens. Dissolved gases come out of solution. Seawater has dissolved nitrogen, oxygen, carbon dioxide. The amount of gas that can stay dissolved depends on pressure. Lower the pressure and the gas starts forming tiny bubbles. This is the exact same physics as opening a bottle of champagne. You release the pressure and the dissolved carbon dioxide forms bubbles and rushes out. In 1 second, the effect is tiny. Microscopic bubbles forming at maybe a few hundred meters depth. Nobody on the surface would notice. But if you were diving at 30 or 40 meters, you might see the water around you start to fizz. Just slightly. Bubbles appearing from nothing. An eerie, quiet effervescence in water that was perfectly clear a moment ago. When gravity comes back, the pressure snaps back to normal, and those bubbles collapse. But some of the gas might not redissolve immediately. For minutes afterward, the ocean would be very slightly more bubbly than usual. Tiny microbubbles persisting in the water column. Layer 4. And this is where people start to feel uncomfortable. The ground beneath your feet. The Earth is not a solid ball in the way an iron cannonball is solid. It has structure. Layers. The crust, the outermost layer, is thin. Under the continents, maybe 30 to 50 kilometers thick. Under the oceans, just 5 to 10. Below that, the mantle, nearly 3,000 kilometers of rock that behaves like a solid over short timescales, seconds, minutes, but flows like an incredibly thick liquid over millions of years. Below that, the outer core, liquid iron and nickel, churning with convection currents that generate Earth's magnetic field. And at the very center, the inner core, a solid ball of iron about the size of the moon, squeezed into solidity by unimaginable pressure, roughly 360 billion pascals. Every one of these layers exists because of gravity. By gravity sorted them, the heaviest stuff, iron, sank to the center during the early molten period of Earth's formation. The lighter silicate rocks floated to the top. That's why we have a metal core and a rocky crust. Gravity organized it by density, and gravity keeps it organized by maintaining pressure. The inner core is solid, not because it's cold, it's actually extremely hot, about 5,000 degrees Celsius, as hot as the surface of the sun, but because the pressure is so enormous that the iron atoms are forced into a solid crystal structure despite the heat. Remove gravity, and what happens to this structure? In 1 second, not much changes in the deep interior. The speed of sound in Earth's core is about 10 to 11 kilometers per second. In 1 second, the no-gravity signal can penetrate about 10 to 11 kilometers into the Earth from the surface. That doesn't even get through the crust in most places. The mantle, the outer core, the inner core, they have no idea gravity is gone. They're still under the same pressure, still in the same state. But the surface, the crust, that top 10 kilometers or so, that changes. Right now, the crust is under compressive stress from its own weight. Rock layers are pressed together. Faults, the cracks where tectonic plates meet or where stress has fractured the rock, are held shut by the weight of the rock above them. Geologists call this lithostatic pressure. It's like putting a heavy book on top of a stack of paper. The paper can't slide because the book is holding it down. Take the book away, and the sheets can slip. In that 1 second, the top several kilometers of crust experience a sudden reduction in lithostatic pressure. Faults that were critically stressed, just barely locked, might slip. Not all of them, not even most of them, but a few, somewhere, the ones right at the edge, might release. These would be tiny slips. Magnitude 1, maybe magnitude 2. Nothing you'd feel on the surface. But seismographs would detect them. And the slips would happen at the same moment all over the planet, wherever faults were critically loaded. A global whisper of tiny earthquakes. Here's the part that really gets me. Volcanoes. A volcano erupts when magma beneath the surface has enough pressure to break through the rock above it. The rock above acts like a cap. Its weight created by gravity holds the magma down. It's a pressure balance. If the magma pressure exceeds the rock weight, boom, eruption. If the rock weight exceeds the magma pressure, the volcano stays quiet. Reduce gravity to zero, and you've just taken the cap off. For 1 second, every volcano on Earth has its restraining force removed. Magma chambers that were just barely held in check feel a momentary release. Now, magma is viscous, very viscous. It doesn't move fast. In 1 second, it can't rise far, maybe a few meters at most in the most fluid basaltic systems, much less in thicker magmas. So no volcano is going to erupt because of 1 second of zero gravity. But the magma shifts. It pushes a little higher, cracks open fractionally. When gravity comes back and the weight slams back down, those cracks might not close perfectly. The rock has been ever so slightly weakened. A volcano that was going to erupt in 3 months might now erupt in 2 months and 29 days. You'd never trace it back to the cause, but the physics is there. Layer 5, let me zoom way out now. The Earth orbiting the Sun. Right now we're moving at about 30 kilometers per second. That's roughly 67,000 miles per hour. The reason this speed doesn't carry us away into interstellar space is that the Sun's gravity is constantly tugging us inward, bending our straight-line path into a nearly circular orbit. Here's a way to think about orbits that I find very helpful. Imagine you're on a hilltop, and you throw a ball horizontally. It arcs down and hits the ground some distance away. Throw it faster, it goes farther before hitting the ground. Now throw it really fast, absurdly fast, so fast that as the ball curves downward, the ground curves away beneath it at the same rate. The ball keeps falling, but the ground keeps curving away and the ball never lands. That's an orbit. It's falling, perpetually. The moon is falling toward the Earth right now. It's been falling for 4.5 billion years. It just keeps missing. Turn off gravity, and the Earth stops falling toward the Sun. For that 1 second, we travel in a straight line, a tangent to our orbit. How much does this matter? Let me work it out in rough terms. The Earth's orbital radius is about 150 million kilometers. The gravitational acceleration from the Sun at that distance is about 6 millimeters per second squared. In 1 second, the Earth would have fallen toward the Sun by about 3 millimeters. Instead, it travels straight, so the deviation from the normal orbit is about 3 millimeters. 3 millimeters in a path that spans almost 1 billion kilometers. It's like driving across the entire United States and drifting off course by the width of a hair. When gravity comes back, the Earth resumes orbiting, but in a very slightly different orbit. Imperceptibly different. Over the course of a year, the change might shift our distance from the Sun by a few meters at most. The seasons would be unchanged. The climate would be unaffected. The orbit survives. But let me push one more step outward. What about the Sun itself? The Sun is a ball of hot gas, mostly hydrogen and helium, held together by its own gravity. At its core, the temperature is about 15 million degrees Celsius, and the pressure is about 250 billion atmospheres. Under those conditions, hydrogen nuclei smash together and fuse into helium, releasing energy. That's what makes the Sun shine. Every second, the Sun converts about 4 million tons of mass into pure energy, following Einstein's famous relation between mass and energy. 4 million tons every second, and it's been doing this for 4.5 billion years. It has enough fuel for about another 5 billion. But here's the critical balance. The Sun doesn't explode because gravity squeezes it inward with exactly enough force to counterbalance the outward push of all that thermonuclear fury. This balance has a name. It's called hydrostatic equilibrium. It's a tug of war. Radiation pressure and thermal gas pressure push outward. Gravity pushes inward. The two forces match at every layer, from the core to the surface. The result is a stable, steady star. This equilibrium is self-regulating. If the Sun contracted slightly, the core would get hotter and denser, fusion would speed up, and the extra outward pressure would push it back out. If the Sun expanded slightly, the core would cool, fusion would slow, and gravity would pull it back in. The Sun is like a thermostat. It adjusts, it finds its balance. Turn off gravity, and you've broken the thermostat. The outward pressure wins. The Sun starts expanding. In 1 second, how far? Well, the speed of sound in the Sun's interior is a few hundred kilometers per second. The gravity is off signal travels inward at that speed. In 1 second, the outer layers of the Sun begin to expand. Not violently, not like an explosion, but they begin puffing outward. The surface of the Sun might move outward by a few hundred meters, maybe a kilometer. It's tiny compared to the Sun's 700,000 kilometer radius. A rounding error. But if the second lasted longer, minutes, hours, the Sun would swell. It would become dimmer and cooler as it expanded. Eventually, the core density would drop enough that nuclear fusion sputtered and slowed. The Sun would become a vast, diffuse, cooling cloud of gas. In 1 second, none of that happens. But the Sun shivers. It twitches outward like someone startled from sleep. And when gravity comes back, it contracts, overshoots slightly, then oscillates. The Sun rings like a bell, too. We actually observe this all the time. It's called helioseismology. The Sun is constantly vibrating at millions of different frequencies. Our gravity holiday would add one more set of vibrations to the cacophony. And now I want to go somewhere deeper. Somewhere most people don't expect a conversation about floating coffee cups to go. What is gravity, actually? Not what does it do, but what is it? Newton said gravity is a force, a pull between masses. Everything with mass attracts everything else with mass. The force is proportional to the product of the two masses and inversely proportional to the square of the distance between them. That law is spectacularly successful. It predicted the existence of Neptune before anyone saw it, because astronomers noticed Uranus wobbling in a way that only made sense if an unseen planet was tugging on it. They calculated where the planet should be using Newton's law, pointed a telescope at that patch of sky, and there it was. Think about the audacity of that. They used a mathematical formula to predict the existence of a world no one had ever seen, and they were right. It put men on the moon. Every bridge, every satellite, every ballistic trajectory ever calculated uses Newton's gravity. But Newton was troubled by his own theory. Deeply troubled. And the thing that bothered him was the simplest question you could ask. How does the Sun pull the Earth? There's nothing between them. No rope, No chain, no rod. 150 million kilometers of empty vacuum. And somehow the sun reaches across all of it and tugs instantaneously too in Newton's theory. If the sun suddenly moved, the gravitational effect would reach the Earth immediately. No delay, no signal, no mechanism. Just spooky, instantaneous influence across vast emptiness. Newton hated this. He called it action at a distance. And he found it philosophically repugnant. In a famous letter, he wrote something to the effect of that one body should act upon another at a distance through a vacuum without the mediation of anything else is to me so great an absurdity that I believe no man who has a competent faculty of thinking can ever fall into it, and yet his own theory required exactly this absurdity. He gave us the equation because it worked, but he couldn't explain why it worked. He wrote, "I frame no hypotheses." He gave us the formula and left the mechanism as an open wound in physics. For over 2 centuries, that wound stayed open. Physicists used Newton's gravity with spectacular success and tried not to think too hard about the how. There were attempts. People proposed that space was filled with some invisible substance, an ether, that transmitted the gravitational influence. Others suggested that gravity was carried by particles. Nothing worked. Nothing explained it. Then Einstein came along and he didn't patch the wound. He replaced the entire framework. Gravity, he said, is not a force at all. It's geometry. This is 1915. Einstein publishes his general theory of relativity, and it says something so radical that even Einstein himself took years to fully accept all its implications. Picture a trampoline, the heavy rubber sheet kind. Put a bowling ball in the middle. The sheet sags. Now roll a marble across the sheet. The marble curves toward the bowling ball, not because the bowling ball is pulling it, but because the marble is following the curve of the sheet. From above, it looks like attraction. From the side, you can see it's just geometry. The marble is going straight in the sense that it's following the shortest path available to it. But the shortest path on a curved surface is itself curved. Now replace the trampoline with 4-dimensional spacetime. Replace the bowling ball with the sun. Replace the marble with the Earth. The sun warps spacetime around it, and the Earth follows the straightest possible path through that curved spacetime. Mathematicians call that path a geodesic. It looks like an ellipse to us, living inside the curved space, but from the perspective of the mathematics, the Earth is going as straight as it can. It's not being pulled, it's not being pushed, it's coasting, freely falling through a landscape that has been bent by mass. And let me be honest about the trampoline analogy. It's helpful, but it cheats. The trampoline analogy uses gravity, the pull of Earth on the bowling ball, to explain gravity. That's circular. The real theory doesn't need a pre-existing gravity. Space-time curves because mass and energy are present. Period. The curvature is gravity. They're the same thing. This isn't just a clever reinterpretation that gives the same answers as Newton. It makes different predictions, and those predictions have been confirmed over and over. The bending of starlight around the sun, first observed during the solar eclipse of 1919 by Arthur Eddington's expedition, confirmed. The precession of Mercury's orbit, a tiny extra rotation that Newton's theory couldn't account for, but Einstein's nailed to 6 decimal places, confirmed. Gravitational time dilation, confirmed. Gravitational waves, ripples in space-time itself, predicted by Einstein, and finally detected in 2015 by the LIGO experiment, confirmed. The shadow of a black hole, imaged in 2019, confirmed. And this brings me to the most mind-bending consequence of our thought experiment. If gravity is the curvature of space-time, then turning off gravity means flattening space-time. Smoothing out all the dimples, all the warps, all the curves that every piece of mass in the universe creates. For 1 second, space-time goes flat. And flat space-time has a consequence that might shock you. Right now, time runs at different rates in different places. Not because clocks are broken, because time itself is stretched by gravity. At the surface of the Earth, time runs slower than it does in orbit. The clocks on GPS satellites tick faster than clocks on the ground by about 38 microseconds per day. If GPS engineers didn't correct for this, your position would drift by about 10 kilometers per day. This is not theoretical. This is the engineering reality of every phone navigation system in the world. Near a black hole, the effect is extreme. Time nearly stops at the event horizon relative to a distant observer. But even on Earth, it's there. A clock on the ground floor of a building ticks more slowly than a clock on the top floor. The The difference is incredibly small, about 1 part in 10 to the 16th power per meter of height, but it's been measured with optical atomic clocks. It's real, flattens spacetime for 1 second, and gravitational time dilation vanishes. Every clock in the universe, from the clock crushed against a neutron star's surface to the clock floating in the void between galaxies, they all briefly tick at exactly the same rate. For 1 second, the universe has a single universal clock, a single tempo, a single rhythm, and then gravity comes back and the warps reappear and every clock goes back to its own private beat. I find that extraordinary. People think of gravity as the thing that makes apples fall. But gravity is also the thing that makes time uneven. It's the reason why now doesn't mean the same thing in different places. Turning it off even for a second gives the universe a brief, unprecedented moment of temporal unanimity. Every point in space experiencing duration at the same rate. It has probably never happened since the universe began. If it could happen, now let me bring it all back. Gravity comes back after 1 second. What's the total damage? Everything falls. Simultaneously. All at once. You drop about 1 centimeter. That's a stub toe level impact. Annoying, survivable, unless you were mid-jump or on a ladder or riding a bicycle, in which case your 1 second of confused weightlessness probably sent you in an awkward direction, and now you're falling from a slightly different position than you expected. There would be injuries, car accidents, because drivers who were mid-turn felt the steering go strange and their bodies lifted slightly from the seat, people on stairs who stumbled when their sense of down vanished and returned, a few drops in places where someone was carrying something heavy and lost their balance. Surgeons mid-operation would have felt their hands drift. Assembly workers on factory floors would have seen tools float off workbenches. Millions of small disruptions, all at the same instant, all around the world. Now think about everything that was resting on something else. Every glass on every shelf, every book on every table, every pot on every stove. During the gravity off second, these objects drifted, just slightly, a few millimeters in whatever direction the residual forces pushed them. When gravity returns, they don't land in exactly the same position. They land a millimeter to the left, or half a millimeter forward, or rotated by the tiniest fraction of a degree. Normally this wouldn't matter, but a glass that was sitting safely in the center of a shelf might now be sitting with its edge slightly over the side. A pot might have shifted just enough that its handle hangs differently. In the first few minutes after gravity returns, you'd hear crashes, things falling off shelves, objects that were balanced precariously losing their balance, not because of the fall, but because of the return, because everything came back to its resting place just slightly wrong. The atmosphere compresses back to its normal gradient. This creates a global pressure pulse, a thump, not violent. You might feel your ears pop. You'd hear a deep, low rumble, like distant thunder, but coming from everywhere at once. This pressure wave would propagate through the atmosphere at the speed of sound, about 340 meters per second, circling the globe in about 33 hours. The oceans slap back into their basins. On the open ocean, this is a gentle swell. At coastlines, confused surges create strange, choppy waves. Boats rock violently. Some harbors see water levels jump a few centimeters in odd directions and then settle. The crust. This is the serious part. All those faults that micro-slipped, some of them don't reverse cleanly when gravity comes back. The stress relief was asymmetric. Friction ratcheted the fault surfaces into new positions. When gravity recompresses everything, the stresses redistribute slightly differently than before. Seismographs worldwide would go haywire. Not from one big earthquake, but from thousands of tiny ones, all at the same instant. Magnitude 1, 2, maybe a 3 or 4 at some critically loaded fault. The combined effect would be detected as a strange, simultaneous global seismic hum. And the Earth itself would ring. These are called free oscillations of the Earth, and we've measured them after large earthquakes. The planet vibrates at specific frequencies, like a bell. The lowest mode has a period of about 54 minutes. The gravity interruption would excite these modes, gently. For hours afterward, the planet would be vibrating at frequencies too low for you to hear, but detectable by instruments. The Earth humming to itself, trying to settle back to equilibrium. Within an hour, most of this calms down. The atmosphere reestablishes its pressure gradient. The oceans smooth out. The seismic ringing fades. The orbital deviation is so small, it's lost in the noise of normal gravitational perturbations from the Moon, Jupiter, and everything else. And life? Humans? Animals, plants, almost all find the 1 second of weightlessness and the 1 centimeter drop are annoying, not catastrophic. Some people fall, some objects break, glasses crash off shelves for a few minutes afterward. There would be thousands of minor injuries worldwide, a handful of serious ones from bad luck, people in precarious positions at the wrong moment, but civilization continues. And here's what fascinates me about the aftermath. Nobody would even be certain what had happened. The experience was so brief, so universal, so unlike anything in human history, that the first reaction would be confusion, not understanding. Everyone on Earth would have felt something at the same moment. A lurch, a strange floating sensation, then a thud, then the ground trembling. People would call each other, they'd turn on the radio. Did you feel that? What was that? The first theory would be an earthquake. But seismologists would look at their data and be baffled, because the signal came from everywhere at once. Not from a single fault, not propagating from a source point, but simultaneous, global. That doesn't happen with earthquakes. Atmospheric scientists would notice the pressure anomaly. Oceanographers would detect the strange wave patterns. Astronomers over the following months might notice the tiny orbital deviation. Slowly, a picture would emerge. Something happened to gravity. Something brief. Something worldwide. And the scientific community would be torn between astonishment and doubt, because gravity turned off for 1 second sounds like the plot of a bad movie, not a scientific conclusion. It would become one of the great puzzles of physics, of a 1 second event with fingerprints in every branch of science, and no known mechanism that could cause it. And that brings me to the thing I actually want to leave you with. Every layer I peeled back, from the cup on the table, to the air, to the oceans, to the rocks, to the orbit, to the sun, to the very structure of spacetime, every layer showed the same truth. Gravity is not just one force among four. It is the organizing principle of the universe. Electromagnetism builds atoms and molecules. The strong force holds atomic nuclei together. The weak force mediates certain kinds of radioactive decay. All important, but gravity is the architect. Gravity takes the raw materials that the other forces create and builds things with them. It collapses gas clouds into stars. It ignites fusion. It forms planets. It holds atmospheres. It shapes oceans. It creates tides that may have helped life emerge in shallow pools. It bends time itself into the uneven textured fabric that makes the cosmos what it is. And the absurd part, gravity is the weakest. By far. The electromagnetic force between two protons is roughly 10 to the 36 times stronger than the gravitational force between them. That's a 1 with 36 zeros after it. If strength were all that mattered, gravity would be irrelevant. A footnote, a rounding error. But gravity has a trick. It never cancels. Electric charge comes in positive and negative. Bring them together, and they neutralize. A big chunk of matter, like a planet, is almost perfectly electrically neutral. The positive and negative charges balance out. Gravity has no negative version, no anti-gravity. Every bit of mass attracts every other bit of mass, always, everywhere, without exception. It only adds up, it accumulates. Pile enough matter together, enough atoms, enough molecules, and gravity's tiny individual contribution compounds into something overwhelming, something that shapes galaxies. It's like compound interest. Each individual contribution is negligible, laughably small, but given enough material, given enough time, given enough accumulation, the effect is irresistible. A single hydrogen atom exerts a gravitational pull so weak you couldn't detect it with any instrument ever built. But 100 billion hydrogen atoms collapsed into a ball, become a star. 100 billion stars, orbiting a common center, become a galaxy. 100 billion galaxies fill the observable universe, all structured, all organized, all shaped by the weakest force there is. No other force does this. Electromagnetism is a billion times stronger than gravity, but it cancels itself at every opportunity. The strong nuclear force is even stronger, but it barely reaches beyond the boundary of an atomic nucleus. The weak force is feeble and short-ranged. Only gravity has infinite range and no cancellation. It's the tortoise in a universe of hares. It always eventually wins. The weakest force in nature builds every large structure in the universe. Not despite its weakness, but because of its special character. It wins not by being strong, but by being relentless, by never canceling, by always adding up, by being patient beyond any human conception of patience. And one more thing, we do not fully understand it. Einstein's general relativity describes gravity beautifully at large scales. Stars, planets, galaxies, the expansion of the universe. It's been confirmed by every experiment we've thrown at it. Gravitational waves detected in 2015 by LIGO, the image of a black hole's shadow, the precise ticking of atomic clocks. It works. Quantum mechanics describes the other three forces beautifully at small scales. The behavior of electrons, photons, quarks. Every prediction confirmed to absurd precision. But gravity and quantum mechanics do not get along. And this is not a minor disagreement. This is a fundamental incompatibility. In quantum mechanics, forces are carried by particles. Forces are carried by particles. Electromagnetism is carried by photons. The strong nuclear force is carried by gluons. The weak force is carried by W and Z bosons. These force-carrying particles can be described using a mathematical framework called quantum field theory, and the calculations work beautifully. You can compute the magnetic moment of an electron to 10 decimal places, and it matches experiment to 10 decimal places. That's the most precise prediction in the history of science. Naturally, people tried to do the same thing with gravity. They postulated a hypothetical particle called the graviton, a massless particle that carries the gravitational force the way photons carry the electromagnetic force. And they tried to build a quantum field theory around it. The calculations blew up. Infinities appeared everywhere, not the manageable infinities that show up in electromagnetism and can be swept away with a clever mathematical trick called renormalization. Unmanageable infinities. The theory said that certain processes had infinite probability, which is nonsense. The graviton theory, treated the same way as every other successful force theory, produces garbage. The reason, as best we understand it, is that gravity is different from the other forces in a fundamental way. The other forces act within space-time. Electromagnetism plays out on the stage of space-time. The strong force plays out on the same stage. Gravity is the stage. It is space-time. Asking for a quantum theory of gravity is like asking the actors to quantize the theater itself. It's a different kind of problem entirely. Some people have ideas. String theory proposes that at incredibly tiny scales, far smaller than any atom, particles are not points but tiny vibrating strings, and gravity emerges naturally from the vibrations. Loop quantum gravity proposes that space-time itself has a discrete granular structure at the smaller scales, woven from tiny loops. There are others, causal set theory, asymptotic safety. Each offers a possible road toward quantum gravity. None of them makes a clear, testable prediction that we can check with current technology. Not yet. Somewhere down one of those roads, or maybe down a road nobody has even found yet, is the true nature of gravity. What space-time really is, at scales of 10 to the minus 35 meters. Whether it's smooth and continuous or pixelated or something we don't have words for. Whether time and space are fundamental or whether they emerge from something deeper, the way temperature emerges from the motion of atoms. So when I ask, what would happen if gravity turned off for 1 second? I'm asking a question we can partly answer with the physics we have and partly cannot. We know what happens to coffee cups and oceans and orbits. We can calculate those with confidence, but we do not know what it would mean at the deepest level for space-time curvature to simply vanish and return, whether that transition would be smooth or violent, whether it would release energy or absorb it, whether at the quantum level the brief flattening of space-time would create exotic particles or emit some kind of radiation we've never conceived of. Whether the question even makes sense in the final theory, the one we haven't written yet. And that, I think, is the best kind of question. The kind where the answer you can give is fascinating and the answer you cannot give is even more so. Think about this. 1 second, one tick of the clock. The weakest force in the universe takes a momentary nap, and the entire planet shudders, the atmosphere loosens, the oceans twitch, the crust creaks, and the fabric of time itself flattens out. Then it wakes up, and everything goes back to normal, mostly with just the faintest echo of what happened. If something that weak, that quiet, that easy to overlook can hold everything together, what else might you be overlooking? What other quiet, constant, accumulating forces are shaping your world right now, invisible as gravity, holding everything in place? I'd love to hear what you come up with.